Welcome to our last webinars in the series of 4 webinars. And the webinar series was called Essential Sustainable Design Tools for Skills for Today's Building Design Professionals. And again, like we had 3 webinars before. And today's webinar is about indoor comfort and energy savings in residential and commercial buildings. My name is Manfred Sapka. I'm principal of Sustainable Design and Consulting. We do sustainable infrastructure and building design. And I'm also adjunct professor at the School of Architecture at the University of Hawaii here. And I've been teaching and conducting research there for the last couple of years. And the applied research I've been doing there is energy efficiency in buildings and occupant comfort. And you can reach me whenever you have questions. Please reach me at the email below. So today, actually, we are speaking about indoor comfort and healthy buildings. And here's a brief reflection of what I've experienced in the couple of years that I've been working on this specific field. And I think some of you might be also joining in the same problem, where actually you have sometimes a hard case to make the financial, rationale for the sustainable design to the building owner. And this is actually some kind of a challenge, because often we do, pitch our proposal to facility people who are very busy people, and they have been doing management and operating, responsibility to the facility or to the building. And we actually usually don't speak to executives, and where we can make the financial benefit argument. And sometimes we just are not really having all this very hard evidence. So that's actually what I've been looking at, and I've seen that here the new paradigm of the healthy and comfortable and productive building actually will change that. And then I've seen the value of satisfied building occupants in the thermal comfort, for instance, studies I've been doing. And also, like I was, for instance, at a couple of schools where I saw, the very dire environmental conditions in which the people actually had to start to learn. And it was really not very conducive. So you start like, what is it worth to have environmental comfort and healthy? So the third one is leveraging technology, and I've been doing some interesting design in the last couple of years, and some of them were humidity, new ways for humidity control, ventilation studies, and so on. And I got actually in all this research a couple of years back, I saw that there were early articles which raised, concern about a green building solution, energy efficient solution, where they say, if we pursue the same route for a highly energy efficient building, we might actually be in trouble in future, because certain things just have to get energy. So that actually got me thinking. So this is my short story here, and let me just go further, and we'll start our discussion. And the objective of today's webinar, we have to show that we need to reconsider actually indoor comfort and health as we implement energy savings. And what we're going to do today is we're discussing the value proposition of indoor environmental quality, which has not been very clear lately. And we have aspects of indoor environmental quality which affect building energy consumption. And then, of course, we'll be addressing, tangible financial gains from good indoor environmental quality. And I'm going over some example technology that I've been working on to increase indoor environmental quality and avoid using energy penalties. And I think that actually this should be a mantra for us, because we are professionals. We are both very concerned about energy efficiency and conservation. But on the other side, we also should really reconsider and seeing in a new light, what is it to have a healthy and productive building? So let's forge ahead. So the objective of responsible design is really to implement energy efficiency, conservation measures to save energy. but the other one is also to provide healthy and productive indoor environment. So we have to tell us, what actually is the value proposition of indoor environmental quality? And then of course we ask us, what design objectives are the most important, and what design objectives provide more benefits, and how do benefits to the owner and occupant compare? So if we look at decreasing energy use and achieving good indoor environmental quality, we have to balance, because we always come into this kind of discussion, how do we see? Some people have preference, but I think a very balanced approach is appropriate here. So what do building owners and occupants value more? Is it saving energy and energy-related cost, and also mitigate environmental economic impact? It's very important. You see, for instance, at most of the brochures, claiming, and it's very important. I'm also, a very big fan of sustainable design, and we only do projects in sustainable design, and take this actually as a value of the company. Or is it creating a healthy and productive indoor environment, even if it costs energy and money? These two things actually have to be balanced. So cost energy savings are tangible. We know actually at the end of the day, in terms of how many kilowatt hours do we save, for commercial, industrial, how much of demand charge are we avoiding? So these are tangible benefits. We can see how much do we invest and how much actually do we get out of it. On the other side, benefits of good indoor air quality is not easily quantified, and because there are less tangible benefits. So if we actually looking at the current building, we have a problem. And might be a lot of problems, but here's one actually which springs out. Homo sapiens, us, we really are made for outdoor living. But if we see, where actually do we spend most of our time? And it is where most of our time we are spending inside of an artificial environment. So, and there's some statistics, and I have a lot of statistics, and this one really, which caught my attention here, is that we spend actually 90% of the time we spend indoors, but 7% of the time we spend in cars, especially if we are long commute. It might be not for Hawaii, but these are and the rest of the time, which is not much, we spend outdoors. Some people more, some people less, but we're speaking about average here. So one problem is also that the indoor environment is much more prone to accumulation of harmful air constituents. And there are some facts. One of the facts, a person breathes an average more than 15,000 liters of air every day. 15,000 liters, that's a big tank load, and go through our lungs. And as we know, for instance, from shellfish, they're filtering a lot of stuff. They are also very prone to pollutants in the water. So sometimes we should stay away from shellfish. But so we can actually hear this one take as an allergen. So that's actually what happened. A lot of air is going into our body, and therefore pollutants can accumulate. And harmful chemical and organic agents in the air can accumulate indoors and represent a significant hazard for occupants. It's like a sponge. And because a lot of these occurrences are so-called surface active occurrences, so where pollutants are, they could be electrically charged, and the pollutants, the particles and the pollutants are adhering to it. And so they're actually in there, they have to, and when they're getting entrained, they can be, they can be accumulated harm, so to speak. The indoor levels of volatile organic compounds can be 5 times higher than outside. So that's because of the accumulation. And higher indoor humidity levels can increase the outgassing of certain VOCs by as much as 2.6 times. So that's actually, although you have the same kind of VOCs in the material, indoor condition could be, inducing a lot of outgassing, so therefore compounding the risks. The last one is indoor microbes in mechanically ventilated buildings are much more closely related to pathogens than outdoor microbes. In this one, actually, I'm referring to a study which I read recently, where a doctor was actually bringing forward evidence that too dry environment inside of a hospital caused significant problems, and it's an HAI, so hospital-acquired infections. And he actually made the point, or sorry, it was a she actually was making the point that, you know, investment into humidification, not even dehumidification, would actually avoid like millions of dollars. So there actually is a direct financial benefit. So the unhealthy building can carry a price tag. What we said, like there's something like a sick building syndrome, that buildings actually could make us sick. You know, we might not be sick outside, but we get sick inside. And there are multiple possible reasons for that. But in addition to the health thing, we have something else, that unhealthy building lower productivity and are really not fun. And this is a component right now which is not only not important for building owners who have liability, of course, and this is also for companies. And you will see afterwards what that actually can mean for our value proposition. So when we see at the properties of the building that contribute to healthy indoor conditions and good, there are a couple of them. The first one is indoor air quality and quality of water supply. Indoor quality, air quality, of course, that's, you know, the air which we are breathing inside. There's also something like water supply, because we could have like, you know, pipes, you know, which have strange things inside. But right now we are much more concentrating on like air. And the second one is the indoor hydrothermal conditions. This is the thermal comfort and humidity level. And this is a very important issue here. And the last one is something which is not necessarily always seen as important, but it is good nevertheless, lights and daylighting. This, of course, is very important. We'll see afterwards, because we can substitute artificial light with daylighting, but also sound, external views, and biophilia. Biophilia, I had to look up that term. I'm not really like you know, I'm an engineer. I'm always handling like tangible things. So this can be which is something, you know, that plants which are present can actually make us feel better. And it has like an overlying effect. So what are the financial gains from outdoor environmental quality? So we have to look at what kind of you know, value can we attach. And there's, on the one side is residential buildings, there's individual health for the occupants, less health problems, and a larger resale value of the house. If you see that you have some mold before, you might have a hard time to sell this thing. But on the other side, commercial building has much more, you know, got much more attention because of the fact that you can earn money, and you actually have to earn money with your building. So there's immediately, there is something like a financial dimension attached to it. So in the commercial buildings, why it is important, you have a more productive healthy workforce, you have less health-related absentees. And a very important thing, and that actually is Phyllis here can do much more, speak about that, is that studies have shown that you know, companies which actually have great indoor air quality as one of the benefits, you know, have much less problems to retain and to recruit talent. And if we know how much it costs to get new people, new employees up to speed, or to attract good talents, they're in short supply, this will become a very significant factor in the future. So does it pay off making building more healthy and productive? The financial argument, you know, how can we make this argument? And how can we see what is the tangible ROI? And up to a couple of years back, this actually was not on the radar, because of the following fact, you know, that indoor health, indoor environmental quality is not required by code. Like here, it is not required. For instance, there's not something like, you know, the code tells you you have to do such. And for instance, I see that Howard is on the air here with us. I mean, he has been working, diligently about bringing in new energy code, and he knows people have to do it. They don't have any choice in order to follow the code. So it is not right now required that people, for instance, have good indoor environmental quality or even like a thermal comfort. It is not required by code. And it's sometimes hard to see the payback. Why, for instance, should building owners or company executives invest so much into this kinds of technology? And outside people might not see it, if the building is healthy, or not healthy. So you have to find new metrics, but these metrics are actually arising. And, I've been working on this with other people, and we'll be seeing hopefully that very soon, actually, it's spreading out, more professionals will be using it. So therefore, the healthy building argument is not yet on the immediate radar of the building professional. So what actually is the cost of doing business? And if you think about what actually have companies to pay in order to conduct their business. And I'm not speaking about, certain warehouse stuff, but it's like an office environment. And in our day and age, actually, like people have to be, good place to work there. They have to be high cognitive facilities there, faculties. So 90% of the cost is actually for personnel. It's productivity, absentees, health-related cost, everything goes into there. And 9% is for rent and office infrastructure and technology, and 1%, as an average, is going to cost for energy. In Hawaii, maybe a little bit better because our energy costs are so high. Maybe we have 3%. But you see actually the magnitude of costs of doing business. So the argument to make to the top executives, the chief financial officer, in order to save energy, sometimes might be a little bit hard to do. So we actually have to have other routes and right now arguments available. So the making business case, is, for personnel costs, typically significant outweigh energy costs. So if we can say, for instance, let's increase the productivity of the workforce by 10%, is probably much more in terms of financial benefits, more than increasing your energy efficiency by 50%. And get me right, I'm not here speaking about do not want to make the case that we do not have to care about energy efficiency and saving. Quite the contrary. We have to be really diligent. It's very important for Hawaii. It's very important for the world. It's very important that actually our kids will still be able to inhabit our planet. So it's serious. So there has been a Harvard, one of many, that's a Harvard building program initiatives. They say that actually they came up with a cost and say, it's about $6,500 per employee, comes from increased productivity and lower cost through increased ventilation. So that's actually referred to, indoor air quality and the related problems. And it's a very good reference. They have been coming out with great information. You can actually look it up. So there has been some research and just put something together. I'm right now writing a paper, so you will be able to see this in the near future. And here's some example how actually it was found that there are some benefits from good indoor environmental quality. The first one is ventilation. And again, these are just numbers. And I have a group of, a bunch of research, and here I give you a range. Some say 8%, some 11%. It really depends on the situation. But here you see improved ventilation can contribute to gains up to 8 to 11% of productivity. It's significant. And he also say thermal comfort actually, is it's very conducive for indoor environment. Well, interestingly, actually, it says, the 4% reduction only if cooler temperatures. So if you overcool your building, you get less reduction in productivity than if you have a warmer temperature. So, but again, this is findings, and very important is about the logical thinking and percent in repetitive office work. Some more examples. Ready for that? So external views, and we have like, if we have better views outside, makes us happy, brings us closer to nature. Here they say 7 to 12% people could actually work faster. There was in a call center. Lights, especially daylighting, you know, it's very conducive. It's also a circadian rhythm. We know all that kind of stuff, that we have our internal clock is always set in the correct way. And so good views, quality, daylighting reduces sick leave of employees by as much as 6.5%. Noise is also a big issue that they said 66%, I'm just quoting. And when exposed to distractive noise, and we did a study also at the UH there, where we wanted to have a natural ventilation. And one of the biggest complaints was noise, not necessarily. It was also pretty hot in there and humid, but noise was, and dust was also a significant complaint. Views in biophilia, we said already, this means affinity to nature, and it's just amazingly nice to see, you know, new architecture springing up and having green walls, and you know, it's just nice to see. It really feels good to be in that kind of. And an interesting study was also that if you have good biophilia, that some of the aspects which could result into unsatisfactory indoor comfort actually are mitigated, that people are more willing to accept this. So here actually one of the also CO2 and VOC as tracer gases, usually like, you see the standards, it's like, hey, you know, if you have 1,000 ppm of CO2, that's actually acceptable. But, you know, studies have found that even at lower rates, like 600 to 1,000, actually already decrease 600 to 1,000 ppm. And one study in particular said, you know, whatever you have more than 600 or 700 ppm, you already have a significant loss. And very important in there that sometimes it spikes up, specifically in classroom. And they say, you know, when you reach 1,400 ppm, you know, it decreases performance by as much as 50%. And it's very important that, you know, the faculties which we have, which, you know, decrease the most is related to cognitive thinking. So, you know, especially for classrooms where people, you know, the students are there to learn, they should be able to breathe healthy and so actually to learn. So that's also an important thing. So aspects of environmental quality, which also significantly affect building energy consumption. But again, like the focus of our talk here is how can we balance, you know, indoor environmental quality, but not, you know, get like a lot of big penalties in order to implement technologies which then would be necessary, for instance, to higher ventilation and so on. So indoor air quality, increase energy for mechanical ventilation, you know, and thermal comfort, provide good indoor thermal comfort, requires cooling capacity. That's normally is like, hey, whenever you want to cool people, just cool them. If they feel cold, they can dress up. But so there's always a technology solution. Humidity is same thing, is connected to the AC, where we have like the conventional ACs that we require very cold surfaces in order to dehumidify, and light and daylight. So we'll be concentrating on these four issues. So they have the intersection between indoor comfort and quality and energy savings. And again, we have to balance it. I think that's a very important, and I cannot stress it too much. It's not either or, it should be both. So we saw that again, like for instance, high, you know, sufficient ventilation can expel a high concentration of CO2 and volatile organic compounds here. And there we made in one of our papers, recent papers, we made one a calculation here where we said, all right, we compare a conventional, a place with conventional 8,000 square foot office building space, and we compared the conventional indoor with the advanced, and the advanced was advanced humidity control. It has twice as much ventilation. It didn't have any overcooling, and it was very silent. So they had all kinds of bells and whistles which actually contribute to productivity. So what we came up and used actually conservative assumptions for increase of productivity, we came up that the cost savings and increased revenue due to personnel, just to increase of productivity, was about 230,000, and the energy savings was 9,000. So it's a clear difference, but still we were saving energy, you know, relative to the conventional technology. So both is possible, but you can see here like what it could be in a very extreme case. And again, this might be extreme, but sometimes in order to shake up people, you have to be extreme and say, not being outrageous, it still is true, but that's the issue here. So when we speak about ventilation, for instance, we of course have two ways. We can have mechanical ventilation, where we actually use a lot of energy in order to ventilate. And you see the new IECC actually is going to require ventilation even in regular buildings. And there's actually this, you see that, you know, the connection is done. Like, you know, it's not necessarily energy conservation, because, you know, if you require energy, mechanical ventilation, you immediately, you know, impose an energy penalty, so to speak. So it is up to the designer, building designer and operator, to be very vigilant and just to come up with good solutions which make both good indoor quality and also save energy. The other things, of course, is a naturally ventilation system, which a lot of houses here have in Hawaii. And so this one was indoor air quality. Right now, just jump very quickly to thermal comfort and what it actually is. So our body is like a heat machine. You know, it creates a lot of metabolic heat while doing things, and it is dependent on the level of activity. The more active we are, the more heat we are producing. And this actually heat has to be lost to the outside. How can we do this here? And we have to look into, because we also have to see how can we design a very intelligent AC in order to have good thermal comfort. And four main mechanisms in two categories. We have perspiration, it's the latent heat loss, and sensible heat loss is convection and conduction and radiation. And here, please don't be you know, concerned. It's not nuclear radiation. It's just this is like infrared radiation, which actually expels heat from the body. Just briefly going through what kind of that we visualize these kind of modes of thermal losses. Is we have here a convective heat transfer, where we have like a lot of heat going over our body, and the more heat and the higher the flow rate, the more cooling is concerned. We probably all know that here in Hawaii. And so evaporative is that, you know, the heat actually is not transferred to something else. It's not a sensible heat, but it's a latent heat loss, meaning that the heat is used to force a phase change. And here, heat is used to evaporate all these little droplets on our skin. So we are losing a lot of heat, very effective. The next one is, you know, the radiant heat transfer, that we have infrared rate, and it goes from the hotter to the colder body. So again, like, it's sensible, because in a sensor, we always have to have a temperature difference from the higher temperature to the lower temperature. Cannot go up. It would contradict thermodynamics. So that actually is here, and usually that feels good, and it's also the most effective way. And important to say, this one does not require any kind of contact or flowing air and fluid. This actually is can even having in through vacuum. But what we cannot have is some kind of a barrier. We as a matter of fact, we have to see the cold surface. Otherwise, we cannot have radiant cooling. And here we have heat transfer through contact and objects, which is conductive heat transfer. That is actually usually not used as a design tool. So if we compare and rule out the conductive heat transfer, we have three left. This is evaporative heat transfer, convective, and radiant heat transfer. And actually for a situation in an office building with low metabolic rates between 1 and 1.2 MET here, is that there is some kind of a ideal combination of these three modes of losing heat. And we have evaporative heat transfer, which would be ideal, about 18 to 20%, convective 30 to 35, and radiative heat transfer is 45 to 50. And that actually here, the radiative is symbolized by a block of ice. Of course, usually it's not one block of ice, it could be just a cold wall or cold ceiling. And if we use like what we see afterwards, radiant cooling, that's actually what we do. I think important to see here is also that radiant heat transfer is actually the most preferred way for humans to expel heat. But our conventional AC does not really, you know, dovetail that kind of preference, because it mostly is concerned about pushing cold air over us and thereby overcooling very frequently. So how is thermal comfort measured? I don't want to go into details. You can all look it up in ASHRAE 55, but we basically have two modes of thermal comfort metrics. One is for mechanical cooling, so for rooms with mechanical coolings, that what's we call predicted mean vote, a PMV approach. And the other one is the adaptive comfort approach. So where we actually have, there's no energy required for natural cooling, whereas the other one, of course, requires it. So in the PMV method, we do have like values, the scales of 6 comfort levels, and the 7th is neutral. So +3 is very hot and -3 is very cold. So whatever is in between, but we should be not further away than -1 or +1. So we have, there's a certain small range which we have to maintain in order to have a predicted good thermal comfort. And there are certain elements which help us. 2 of them are individual thermal conditions, which is like clothing and metabolic rate. When we, again, like when we do a lot of exercises, we have a lot of heat going up. The other one is clothing, you know, which is forming insulation for our heat transfer to the outside. So it is impeding. On the other side, which is actually representative for the entire space, is air temperature, mean radiant temperature, humidity, and air velocity. So these 6 metrics are put together, and then, you know, we can calculate a PMV, which is the predicted mean vote, and it has to be between a certain numbers, -5 to +5. So from that, actually, and the next step is to correlate how big the predicted percentage of dissatisfied occupants are. And it has to be under or maximum 10% in terms of general comfort. So that's how we, in a nutshell, we do it there. The other one is, you know, adaptive comfort, where we actually have to see that there is a combination of prevailing mean outdoor temperature and the acute operative temperature indoor, and it has to fall into certain probability or acceptable range. If we're inside of the range, like this red dot is there, we are compliant. If we are outside, we are not compliant. So again, like, you know, we in the adaptive, it's kind of interesting that we see that we have prevailing mean outdoor temperature, which is like we're going back and seeing what was the temperature in the last 10 or 20 years, because our body can adapt. And then when we adapt the better to heat to hot outside temperature, we can actually stand better indoor operative temperatures. So right now, one of the big thing here in Hawaii actually is the gorilla in the room is humidity. And it's different from thermal comfort. Humidity is not only, you know, making it muggy, it also has certain health aspects, especially if we have condensation. And, you know, then we have this very, you know, you just have to mention mold in like to a operator, so they will just, will not be happy. So we have to control humidity. And that's actually a big problem, because if we right now, we seal up our buildings, we are getting more and more humidity problems. And there's an optimum range of humidity, which is between 45 and 55. New studies have indicated actually should be less. It should be about between 40 and 50%. So there's still some, you know, discussions going on. But about 45% is probably pretty good. But right now we have sometimes much higher indoor humidity level. And because to dehumidify is also taking a lot of electricity. And we can dehumidify like our indoor space either with a dedicated heat and dehumidification device, or we have it with our space AC system. And And last but not least, we have like light and daylighting, which is important for our comfort and health situation inside. But it also helps us to save energy, because if we have a lot of daylighting, we can actually replace, you know, some of the lighting, you know, with daylighting. So it makes us more healthy, and it's better for the energy cost. So right now, just briefly, I would like to go over some example technologies which actually increase the indoor environmental quality and also use less energy. And here we have 4. There are a couple of more, but I think this one I like the best. This one is, the first one is advanced gentle AC, and this is hydronic water-based cooling. I will be going this very briefly. We have dedicated dehumidification, so that actually we can control the humidity level inside of the space better. We have total energy recovery. So when we have this one, we can recover energy, but also still, you know, increase the ventilation. And we have a ceiling fan. And again, like, ceiling fans are just great for us. We should really use it more. And Howard actually has made sure that in future, we have to at least, you know, fit in such a way that we can put in ceiling fans easily. So the first example is what we call the advanced smooth AC. It's chilled beam or radiant sealing, where we actually actively cool ceilings. And we can have either radiant ceilings or chilled beams. You see in the left radiant cooling ceilings, and on the right chilled beams. And there's been some fantastic new technology, which is passive chilled beams. They're very, very energy efficient. And they are also very efficient in terms of moving air, you know, passively, and also mimicking chilled ceilings. And how it works is actually we have like a the chilled beam here, you know, it puts into motion the internal circulation of air, but we're also radiating heat, you know, from our body. And the big difference between the conventional conventional air conditioning is that we are pumping water, pumping the temperature, not by air, but by water. And how it works here, you see actually we have heat internally, and we have to get rid of the heat and transport it to the outside. And chilled water is much more effective to transport and pump heat than air. So here just a short, I just made a calculation also with the help of some students 2 years ago. And if we want to transport the same amount of heat with chilled air, which in regular air conditioning, or we want to do it through a heat transport through water. So these big ducts can transport the same kind of heat. And the one side we have elaborate ductwork. We can have also growth in there, big health problem. And we also have the big ventilation fan on the right side, and water is much more effective to transport by pushing, you know, the water through with a pump. So the pump power needs and high fan power needs compared makes a big argument for hydronic systems. So the next one is dedicated dehumidification, and the big thing right now, it's actually a good movement, and I've been seeing it more and more, and where we decouple sensible and latent cooling. And basically it works like that, you know, in conventional buildings, we actually cannot decouple latent and sensible cooling, because we're passing the air over a chilled coil. And since it is below dew point, you know, the water condenses, it actually accumulates on the coil and then just drops down into a pan. And that's how we dehumidify. And sometimes it's so cold that we have to reheat the heat, because, you know, we have to have it cold in order to dehumidify. So the better thing is actually by decoupling it, and we can accomplish this by having above dew point sensible cooling and above dew point sensible, above dew point dehumidification. And here typically we've been using desiccants. So much better, we can actually control humidity levels individually from sensible cooling, and this will be a very big energy saver. And what we did was we used technology which has the big advantage. We can also use solar heat. we calculated is up to 70% of the loads we can save in relative to conventional AC loads. It's some kind of evolving. There have been some commercial installations on the mainland and which are successful, but it's still like a technology incoming. So that's very promising. So total energy recovery, I think, you know, we know about what that is. We have something, since the indoor air is cold and low in humidity, we can actually use this air as a sink, not only for heat, but also for humidity. And it has been like, probably some people, you are familiar with the big desiccant wheels and all kinds of stuff. And it was pretty effective already, but used a lot of hardware. And they have come up with this really nice total energy exchanger. These are cubes, and they're just working fantastic. So we can really cut down a lot in terms of energy. And I say total energy is sensible. So we have to cool the air and we have to dehumidify the air. So this one doesn't recover total energy, but we can easily, you know, achieve something like 60% or whatever. So sensible usually is a little bit higher than latent. So in order to pass the humidity back and forth is a little bit less effective than sensor, but still big energy saver. And the last one is the ceiling fan, and the ceiling fan is providing actually cooling, but it's localized and cooling, and it also avoids what we call the thermal boredom, because if you always are very cold, humans actually like variations, and variations is like sometimes they would like to have a little bit more air flowing over their body and sometimes less. So the cooling effect through increased airspeed by ceiling fan is really nice, very promising. And you see on the lower right one is actually the airspeed, and you can correlate to a temperature rise and increase in acceptable operative temperature limits. So, and advanced ceiling, we have used that actually here at the University of Hawaii, some of the new ceiling fans with very strange names, but very good. And they can actually provide a fraction of, they can save, significant cooling energy by providing the occupant with a cooling effect. But here the cooling effect is not translated to, it's not translated to actually lowering the temperature in the room. It's really like, it's a cooling effect only for occupants, because the cooling effect is air flowing over the occupant's body. So, and again, like we have seen here, you see one of the recent investigation we have done at the University of Hawaii, where we used computational fluid dynamics in order to see, hey, what is the flow rate simulated, and then we checked it how it was good, and it was fairly good coincidence here in terms of data. So we are really happy with that, and we cannot overemphasize how good ceiling fans would be here, just doing bigger use. It can really help us a lot. So right now, actually, we summarize, and so we saw the financial incentives, to the building owner and companies of good indoor air quality. And we have to see that it's a very powerful way just to advance the green technologies. And so we see that they can actually outperform, the cost for energy savings. But energy savings are right now, they are required by code, so people have to do it. But I think our responsibility of innovative and responsible designers and building industry professional would be to bring both, just being good in energy savings, but also have a very good demand on what is indoor environmental quality and what is health, because that most likely will be one of the decisive decision making in the future. And again, like here, what I said, like the innovative building technology and design strategies can actually avoid energy penalties. So that's the good news. We're getting smarter. and we can only offer, you know, and we can pull our comrades in design arms or whatever we want to call, to actually, you know, having better buildings and having better performance buildings, and perform both. Be like financially in terms of energy costs, we can drive it down. We can, you know, we can comply to the energy codes, but on the other side, we can actually build better buildings. So that's basically what I have left here to say. I would suggest that, you know, when you have a question, please email me, and I would be happy to answer every questions you have. And so you see the email in our flyer. It's sustainabledc@gmail.com. And so with this, actually, I would like to stop the webinar and thank everybody for participating. Hope to see you in future. Thank you very much.